All right, so time it takes for a chemical reaction to occur is given by T of A. T is time in minutes, and A is the catalyst used in milliliters, which is a weird independent variable. I mean, in the context, it makes total sense to me, but it's kind of weird compared to other stuff. Yeah. Okay, so interpret T of 40 equal, or T prime, excuse me, of 40 equals 1.7. So first of all, is what we're given a rate already or not a rate already? It is not a rate already. So T prime will be, I guess we could say, the first derivative. That will be the rate. So at 40 minutes,
40 milliliters.
Yeah.
40 milliliters, sorry. ml, if you want to use that abbreviation. Huh?
I said at 40 milliliters of catalyst used.
Yeah.
Just putting.
Okay, sure.
Is that like necessary?
It doesn't hurt, and it doesn't take a lot of time to do. In terms of necessary, I think since you're giving 40 milliliters, and we're not doing 2 milliliters, we're not doing 2 volumes, one's time, it's implied. Yeah. You could even say, because at sounds more like time, so we could say when 40 milliliters of catalyst are used or something, right? There's not just one acceptable way of writing it out. So anyway, the rate, how do I want to say this?
I said the rate of catalyst is 1.7 milliliters per minute.
I said the time it takes for the reaction to occur
is changing
at a rate.
Yeah, so you said catalyst, but it is time. The time of the reaction is dependent on how much catalyst. Do you guys know what a catalyst is?
Yeah, it's like what you use to make the reaction.
It facilitates it, so it makes sense. If you use more, it will occur quicker, and less occur slower. What could that be? Yeah, like, did you ever do vinegar and baking soda? You have it bubble. Like, if there's not enough of one or the other, it doesn't work as well. You could think of it that way. Anyway. The time the reaction takes is changing. It is positive, so it's increasing. There's our phrase, at a rate of 1.7 minutes, and this is the weird part, per what?
Per milliliter.
Yeah. Which sounds super weird, right?
That makes sense because we've done that in chemistry before.
Okay.
So like we calculated how much. What did? We did like hydrochloric acid and salt, and that makes bubbles.
Mm-hmm.
And so like we have to see which one to see how fast we can make the bubbles.
Yeah. Does that help?
Yeah, but I don't know. Would it say? Would you say increasing at a rate of, or would you say that the rate of? I don't know because.
Well,
it's not a second derivative.
Right. So the time that reaction takes is not a rate, right? It's just a time, but the time that it is taking is changing.
Okay.
So it's just at a rate of it would be like velocity, right?
Okay.
It's just a speed, not an acceleration.
Okay.
Yeah, it's a little bit of a weird one. Any others on there? Okay. Good? All right, well, we're going to take that, so flip to 4.2. This is some of the best stuff that we'll do this year, I think. But it's also one of the top topics in the whole course that will be assessed. And you've taken the test, so you probably can affirm that it's on there. A lot of it is on there, right? Like
Yeah.
rectilinear motion.
Yeah.
Okay. A lot of our problems will have to do with this going forward. And fortunately, we've talked about it some to this point. So position, I think I've mentioned this before. Position is most often given by S instead of P of T. So S of T stands for position. And that's true across like calculus and physics. You guys haven't taken physics if I remember right? Yeah. But if you do, you'll see that. Well, you definitely will. You will. Maybe you could take physics when you're learning.
Well, I just took like physics last year.
Oh.
Like the one that.
Okay.
I didn't know, because I didn't know we were talking
Yes. All right. Anyway, so throwing a ball straight up and then catching it. We have this function model. Now we're not going to get too into the super details of that, but S, know that S references position. So, hopefully you remember from like pre-calc and algebra 2 that things tossed or thrown into the air are quadratic, and so they follow that parabolic shape. What would the velocity function look like? Or graph, or the
Down.
why?
Because like it starts going up, but then gravity makes it go slower, so it goes down.
Okay, so, and I don't know if you remember this form of equation, but the 18 is our initial velocity. So whatever we threw it up with. So it starts with an 18 upward, so positive toss. And then, like Christian said, it's continuously going down.
Yeah.
When does it hit a 0 velocity? So use this graph.
Right back to, I could probably before 2 just a little bit.
Yeah, like just maybe here, right? Just before 2. So with those 2 points, then we can connect with a straight line. Something like that. Okay. Oops. So keep in mind, if you're thinking derivative, right? Velocity is derivative of position. This is quadratic, so it should make sense that our derivative is linear, right?
Yep.
Okay? And then how about acceleration? If we found the slope of that line is what acceleration would be. Is it negative or positive?
Negative.
It is negative. And it turns out in these types of equations, that first number is our acceleration due to gravity. And when we get to the integral part of our unit, or of our course, integrals are antiderivatives, we'll see why it's 4.9 and not 9.8. Do you guys know, do you know the number 9.8 meters per second squared? Okay.
Well, I took the derivative of first equation, the double derivative, and I got negative 9.8.
Yeah, and even if you look at the slope going down, like on the graph, you start at 18 and you're going down pretty much too. So it's 18 over 2, which is 9.
Right, but I'm saying we'll see why in the position function this is always half.
Oh.
Like
Should
if
the
we
acceleration be 9.8 on that graph?
Yeah.
I see what you're saying. Yes, it should. Position, like if we did this in English, like imperial units, do you guys know the gravitational acceleration in that unit system?
It would be close to 28, 29.
Yeah, it's like, well, it's 32.2, so you're close. And this is always 16 in the position function. So that part's always half. We'll see that, and yes, you're right, this should be 9.8, okay? So to get A from this is A over 2. All right, so we'll do some relating of graphs. Like we have actually done that. I think we're prepared for it, but we'll do some of that in this section. So position is S, velocity is ds dt. And then if you want your Lagrange notation, s prime of t. Acceleration we know is the double derivative, or second derivative, of the position function with respect to time. Okay? If velocity is less than 0, what is happening? Well, not just necessarily in tossing the
Or
ball,
slowing down.
but in general, if our velocity is negative,
It's slowing down. Or going down.
No.
it may not be slowing down.
It would
We
be
have to be careful. So,
declining in position.
yes, so we'll talk slowing down here. And it'll make sense for sure. But if the velocity is negative, we could be going fast negative or fast in the negative direction, right? So, which way is negative?
Left.
Yeah. So moving left or what? Or down. And it depends. Like this problem up above would be a down problem, so that's a y-axis problem. But moving left, maybe we're talking about a car, maybe, I don't know. But that's an x-axis thing. Okay? How about velocity being positive? Moving right or up. So again, x-axis versus y-axis. So it's important to know the frame of reference that we're looking at. Velocity of 0 means what?
Set inflection.
Not necessarily, but at rest. Okay? So look for words that kind of communicate things like it stopped. Okay? So on our ball toss up, where is the velocity 0? Well, we already said it's at the top where it changes direction. Okay? That would be a y-axis problem. All right, so average velocity, we can do this with, just like we did with like an average position. So average rate of change, do you guys remember AROC or ARC? Average, it's just a slope. So average rate of change. This will look familiar. Just position change and how long it took. Okay? Give me an example from maybe this morning of how you could calculate an average velocity. Tell me about it.
Speeding up and slowing down a lot. So like average velocity at a certain time would be like when I was speeding up it would be higher. Or like when I was going fast it would be higher than when I was like stopped.
Is that more kind of instantaneous?
Well like if you like took like when I was driving like if we took the average velocity when I was driving on the highway
Okay.
versus like when I was back
Okay.
driving.
Hopefully you don't drive the same. Yeah, or you could even compare it to your whole trip, right? So 6 miles here, it took me 12 minutes or whatever. Okay? Versus just the 2 miles on the highway, and that took 4 minutes or something. Okay. All right. Speed. Anybody remember what we've said about speed versus velocity?
Speed is absolute value.
Okay. So velocity, I want you to kind of put this over here. Velocity has a direction. Sign matters. Okay? In physics, and calculus comes out of physics, it's very closely related, but velocity is a vector quantity. It has a direction and a magnitude. Whereas speed is just a magnitude. So speed is the absolute value of the velocity, just a magnitude. So I could be driving 40 miles an hour west or east. We're not going to say negative or positive. It's just a direction, or a directionless unit. So in physics, speed is called a scalar. I don't know if you're interested in those words. But math on vectors and scalars is different at times. And calculus is different on both of them at times. Okay. So absolute value of the velocity. Alright, here's the speeding up, slowing down stuff. If velocity and acceleration have the same sign, what do you think is happening? Yeah. So one thing that I think sometimes students are confused about, or can be, is we can be going what we consider the negative direction and be speeding up and going fast, if you want to say it that way, right? So relating to driving. If I'm at a light and the light turns green, what do?
Go.
So you accelerate in the same direction as you speed, right? So you're speeding up. As you get to the next light and you hit your brake, tell me about velocity and acceleration in that case.
You're still going in the same direction, but you're still in down.
Okay?
Acceleration is negative, but velocity is still positive.
Yes. So you're accelerating, which sounds weird because we think of the gas pedal as the accelerator, right? But technically your brake is accelerating you, it's just accelerating you in the negative direction from the direction you're going. Okay? So sometimes that takes a little while to reconcile all that. Speeding up could mean that we're going in the negative direction. Faster and faster.
In reverse.
Yeah.
But then you would still have both velocities.
Well,
If
in
you're
that
speeding up in reverse, it doesn't. That's just the position of the car. That's not you going.
you'd have to define in that case a direction that is considered positive and one that's negative. Yeah. Forward would be positive, backward would be negative. Yeah. Or you could do absolute, like if I'm heading east, I'm going positive, west is negative or something. But anyway, if they're different signs, obviously slowing down. So when we're analyzing this, this is what we'll use. In this section, you're going to see a lot of justify, and we haven't done a lot of that yet because we haven't really needed to. But that's going to be the phrase that we use. So justify. Like if it's speeding up, it has the same sign. Are we about done?
I don't know what's
Still
actually.
have 20 minutes.
Yeah, 20. We're good. Well, about 17 minutes. All right, so go ahead and fill out this table. You're just concluding whether it's speeding up or slowing down.
Would be able to go longer so we could actually.
And it didn't help like with retention, but it helps passing them.
True, the retention part is definitely not good.
But as a freshman, I didn't really have to retain much. It was like my freshman classes.
Well, you must have been a freshman with the brain then. That's nuts. You can't say that about everybody.
My freshman year was the only year that I got all A's.
Good
My
job.
sophomore year, I got like 2 B's. My junior year, I kind of fell off here.
So then, I just liked it because I remember my last quarter, my freshman year, I didn't have any math.
Oh,
Or
that's
ELA,
cool.
because that's how it worked out. So then I just had basically electives my last quarter, so I was like cruising.
It was really nice for like band classes too, because like some days I would like, or like the whole quarter I would just have it. It was great.
Yeah.
Yeah, that sounds fun. All right, let's talk displacement.
Okay.
Sometimes this can be kind of confusing. So this is the net, and I want you to underline net. change in position. So if you run the 400, what's your displacement
100 meters.
on a track? I should have said that.
Well, the 400 is 400 meters. not 400. Oh, I guess it.
So your
proves
displacement
point.
is 0
Because it,
because you end where you started. Okay. So it's weird, right? Your total distance that you ran is 400, but your displacement is actually 0. So you have to be careful with how any displacement problems are worded, because if you think like in terms of, let's say you start at home and you go to school, I don't know how far that is for you, but let's say it's 10 miles. And then you come back, where would you go on your way home? Sonic? Grocery store. And that's 3 miles. What's your displacement?
7.
So your displacement, you're 7 miles from home. Okay? And so on the next page, we'll see some questions about that, but like this first one. If we're given this x of t function for particle moving along the x-axis, and then the first question is find the displacement of the particle for the first 2 minutes. How would you do that?
solve for 0, solve for 2.
Good. Find their difference. Real quick, I want you to highlight. Ooh, that gave me the chills.
Yeah, I was
Oh, I need to get a different pen insert. Because sometimes this will be given. I tried to resist, but it didn't. It just kept coming. Sometimes you'll be given, instead of the position function, maybe the velocity function. So you have to read carefully. So, like you said, we'll just do 0, which is just 3. At t equals 0, it's 3. And at t equals, what was the time? 2. So 2 cubed minus 4 times 2 squared plus 3 is, what is that? 8 minus 16, negative 8 plus 5, or plus 3, I mean. Okay, so our displacement is the difference. So x of 2 minus x of 0. And does it tell us any units? Centimeters, yeah. Negative 8 centimeters. Do we need to put per minute or anything on there? So this, go ahead.
Is displacement, isn't that, I might just be remembering wrong, but I thought it was always absolute value. Like, because your displacement is your total distance from where you started, whether it be positive or negative.
So it's not. We need to put a sign, because if you think about moving along the x-axis,
Yeah.
we could end up left of 0 versus right of 0.
Okay.
And I know where you're coming from on that, because displacement is kind of like speed, where we just, how far are we from where we started? Who cares which direction,
Okay.
is what you're saying, right?
Yeah.
Okay. All right, average velocity. So are we taking a derivative?
Yes.
We don't have to.
Well, average velocity.
You give it a position.
So do we have to take a derivative? Well, let me ask it maybe a little bit better way. If I just said what is the velocity, what would you do?
Then you just
You do have to have a derivative for the velocity, right? So if we say average velocity, do you still have to take a derivative?
I mean, it would make it easier to do average velocity. Technically, you could just plug in your points and divide it by your, but it would make it easier to do the derivative.
So for derivative, if you take the derivative and plug in a point, you're finding the
Oh,
derivative, the
instantaneous.
instantaneous velocity at that moment.
So if you're looking for average velocity,
We're just saying position minus position over time change, right?
yeah,
That's the average. We can't say speed because this has a direction, but if you think of it that way, that's the average speed. It's like saying Christian drove from home to school over 15 minutes, right?
yeah.
That's his average velocity. So we don't have to take a derivative. Everybody good on that? So this is going to be s of 2, not s, this is x, but same thing. X of 2 minus x of 0, which we already figured out, divided by 2 minus 0. So this time, negative 8 over 2, negative 4, what units? Yeah. Centimeters per minute. No derivatives needed. But how about here? Velocity at a moment in time. Yes. Now we do need a derivative. So velocity is dx dt. What is that derivative?
Squared minus 8.
And plug in 4. So let's do v of 4. So what is that? 48 minus 32 is 60 centimeters per minute. Okay. Acceleration, how do we get that?
The second derivative.
And that is?
16 minus 8.
Okay. And units? Good. No, that's a fluke that they're the same. It happens occasionally, but it's not like a thing. But they are the same. The velocity and acceleration. Is the particle speeding up or slowing down at t equals 4? Okay, justify. This time we have to write out some sentence words, right? So explain it out. Which one is it, first of all?
Speeding up.
Okay. So time. Let's say time. I'm going to say time. How do you think we could justify that?
Because acceleration and velocity are possible.
Okay, you're right, and it's going to go back to these phrases that we circled because acceleration and velocity have the same sign, okay? That's our justification. Okay. Good so far? Very good. We need to eat some food or something.
No, I'm good.
Okay.
I'm just laughing.
Good. I like locked in. How much time? Oh, we have 3 minutes. So let's save this for tomorrow. And